if you haven't seen my previous videos, I would recommend watching those first. That would just be the part 1 and 2 of the Hyperbolic Trig series. You can still get something out of this video without seeing those, but in order to get the full learning experience, I would recommend watching those first. There's a few things I might talk about in this video that if you're not familiar with the concepts, you might be a little bit lost, and you can learn those things in the first 2 videos. Alright, and welcome back to Pi Guy. So today, I am talking about how you can use hyperbolic trigonometry to do some problem solving, and in this first example, to skip some steps in solving some equations. So here we just have just an equation. We're solving for whatever value of x makes this equation true. So I'll start with the non-hyperbolic trig way, just to provide a comparison for how much shorter and easier the hyperbolic trigonometry way is. So I start by multiplying both sides by e to the x. You multiply the powers on the x's, so you have e to the 2x when you distribute that term in there, and then e to the x and e to the negative x cancel to 1 when you multiply those two terms. And then 3 times e to the x is just 3 to the x. So we have that in that next line there. Then I'm just going to move the 3e to the x over to the left side. So now we have e to the 2x minus 3e to the x plus 1 equals 0. And now what I'm going to do is a substitution where I'm going to let u equals e to the x. So when I factor out an e to the x from, you're just going to factor out e to the x from each of the terms here and replace it with a u. So I factor out e to the x, I get u squared, because e to the 2x is the same thing as e to the x squared because of our properties of exponents. And then obviously, taking the e to the x there, replacing it with u, minus 3u, and then there's no u to take out in the 1 or 0 terms, so you just leave them be. So now we have u squared minus 3u plus 1 equals 0. And then what will happen is we're going to solve it just like we would solve a quadratic equation. So we've got our quadratic equation set up here, u squared minus 3u plus 1 equals 0. And I'm going to plug it into the quadratic formula. I'm not going to bore you with all the steps here. I think most of us know how to use the quadratic formula. So we have negative 3 plus or minus the square root of negative 3 squared minus 4 all over 2. That simplifies to negative 3 plus or minus the square root of 5 over 2. So then we get u equals 2.6180 and u equals 0.3820. Remember, we are solving for u after our substitution. I'm rounding it to 4 decimal places here. That's not the exact value. I'm just rounding. But then remember that we had a substitution where we let u equals e to the x. So now we have to plug e to the x back in and replace it for u. So now you have e to the x equals 2.6180 and e to the x equals 0.3820. And then we take the natural logarithm of both sides. So we have ln 2.6180 and ln 0.3820. And that happens to be positive and negative 0.9624. And that is no coincidence. It's by the properties of one of our hyperbolic trigonometric functions that we end up having, that the natural log of 2 seemingly random numbers is the positive and negative version of the same number. So I'll go into the hyperbolic trig way of solving this, and that will all be revealed. So while that's not a particularly difficult equation to solve, it definitely did have quite a few steps, and especially if you're writing out all your steps for the quadratic formula, it can get a bit lengthy. But luckily, as you can see here, we can shorten it to just a few steps using hyperbolic trigonometry. So we start again with the same equation, e to the x plus e to the negative x equals 3. We recall that the hyperbolic cosine of x is e to the x plus e to the negative x over 2. Now we don't have the negative, or the over 2 here, not negative 2 at all. We don't have the over 2 here, so we have to make sure that it's 2 times the hyperbolic cosine, because if you have 2 times this, the 2 in the denominator would go away, and you just have the e to the x plus e to the negative x like we have here. So we need to make sure that we're doubling that. So now we have 2 times the hyperbolic cosine of x equals 3. And then we divide both sides by 2, and we have the hyperbolic cosine of x equals 3 halves. And then we take the inverse hyperbolic cosine of both sides, because when you take the inverse function of this function here, it'll just cancel to x. Kind of like what I did when I did the long way. I took the natural log of e to the x, so the natural log is the inverse function of e to the x, therefore it cancels back to x. Now we don't have an x or a hyperbolic cosine over here, so that just becomes the inverse hyperbolic cosine of 3/2, which coincidentally is, or not coincidentally, I suppose, is positive or negative 0.9624. I mean that shouldn't be surprising. We did mathematically correct work in both instances, but this is a way that you can use the hyperbolic cosine to skip through a lot of extra steps. Now note this will only work if it's e, but it won't work for any other exponential base. But there's plenty of instances where you'd want to use e, because like I said in the first episode, a lot of real world situations use parabolas that are based on e. So we're going to jump into the graph of the function and see why this is the way that it is. So what we've got here are the graphs of the two equations that we are setting equal to each other in the problem that we worked through earlier, e to the x plus e to the negative x, and y equals 3. And we will see here that the x values at which they touch, therefore the solutions of the equation are the same point, just positive and negative, or the same value, just positive and negative. What we'll notice here is that this does exactly line up with 2 times the hyperbolic cosine of x. I'll turn that one off so you can see. They do line up perfectly there. And this basically means that it's just a dilation of the original hyperbolic cosine graph. So it's just stretched in certain directions somewhat. But its parabolic behavior is still apparent here. We can clearly see why it has the two, just basically a flipped number as its solutions, because it has y-axis symmetry. It's an odd function, or sorry, not an odd function. It's an even function. Therefore, it has y-axis symmetry. And since there's no horizontal or vertical translations going on here, it's gonna maintain that y-axis symmetry. And if it's intersecting with a constant line, that means its intersection points are just going to be the same point, just mirrored. So therefore, positive and negative. This shows a very important property of the hyperbolic cosine function, that it is an even function with a parabolic type shape. So these kinds of equations are going to show up in like the shapes that like suspension bridge cables make, for example, just and other things like that. Things in nature tend to take a more hyperbolic or a parabolic curve that's based on the hyperbolic trig functions more than just straight polynomials. What this also shows us then is that the inverse hyperbolic cosine has 2 solutions, because it, very, very clearly fails the horizontal line test here, which means that its inverse function, or the inverse function of the hyperbolic cosine, won't be a function, thereby meaning that every x could have more than one y. So if we go ahead here and graph the inverse hyperbolic cosine, yeah, okay, well it's graphing only the top half because it wants to make it a function. If I graph the bottom half, there we go. So this entire curve is actually the inverse hyperbolic cosine of x, and so we can see here 3 has 2 solutions. So that's why, if you recall, when we in the equation we're taking the inverse hyperbolic cosine of 3, we got 2 different solutions, and they should match up to what we have here. Oh no, it should be half that, because if you remember, it was 2 times it. We didn't have the divided by 2 part there. The point stands though, that each x on the hyperbolic cosine has 2 y's because of its parabolic shape, because parabolas are not 1-to-1. Now, if you were to have an equation that was e to the x minus e to the negative x, and you were using the method I showed earlier, using hyperbolic sine, you would take the inverse and you would only get 1 solution. So it would be really, if you think about it, then that wouldn't be modeling a quadratic. So really, you couldn't even use a quadratic to solve that kind of equation. There would be an erroneous solution or something like that if you did it in the end. So that's why this will mostly show up for the inverse, or not the inverse, just the regular hyperbolic cosine type of equations, like the one I showed earlier, where this is a plus, not a minus. So yeah, you can use that in all sorts of different equations with e in that setting. On some of them might be more complicated, so you might have to use more complicated algebraic tricks to get it down to the hyperbolic cosine. But that's pretty much it. If you have any questions, you can always leave a comment. And I would encourage you to leave a comment and tell me what kind of videos you'd like me to put on the channel, because there is only one video remaining in the Hyperbolic Trig series, and that's where I'm going to talk about calculus and the derivatives of each of the hyperbolic functions. So I am open to suggestions for video ideas. As always, thank you very, very much for watching. I've been Pie Guy. Have a great day.